Thank you. Welcome, everyone, to the 165th Law Physics webinar. We're very happy to have today Paul Ramond. He is currently a postdoctoral researcher at the University Paris Dauphine, I guess. Maybe Paul can help me to pronounce that. He was a PhD student. He finished his PhD at the University de Diderot, Paris 7. Paul is an expert on various theoretical aspects of gravitational systems, in particular on the relativistic mechanics of black holes and Hamiltonian dynamical systems. Today, he's going to talk about some recent work of him and his collaborators related to the integrability of extended test bodies dynamics around black holes. Paul, thank you for accepting our invitation. Please take it away.
Thank you, Alejandro. Thank you for the introduction. Hi, everyone. I will try to share my screen now. Can everybody see something that has to do with a slide?
Perfect. See, it's
okay. Right. Okay. So I'm going to talk to you about the recent project of mine I've been pursuing with a number of collaborators. And as an introduction, let me start with a bird's view of where I work. So on the right-hand side here, you can see a photo of essentially the place I go to when I go to work in Paris. This orange line you can see is something that goes through France and also a little bit of the UK. That's actually the first historical first meridian. Now, the first meridian goes through Greenwich, as you may know, but there used to be a time where it used to go through Paris. And this castle you can see at the top of the image that goes through the orange line was actually built on this meridian. And this is actually one of the siege of the two spots where the Paris Observatory lies. So this is the Paris spot. And on the left, you can see two labs, one in blue, one in red. The red one you may know as the Institut of Astrophysics in Paris, where many relativistic people do things related to post-Newtonian theory, cosmology, and essentially most people, they are familiar with GR. And on the blue lab, not all people are familiar with GR, especially on my flat where, on my floor, I should say, where everyone on the contrary is very familiar with Hamiltonian mechanics or analytical mechanics, if you prefer. And the core of this project I'm going to tell you about is actually bridging these two communities, these two fields, as you can see on the top left here with these two fists, the one of Poincaré, which represents the Hamiltonian mechanics aspect, and the one of Einstein, which represents the general relativity. So many people have helped me, and we are working together about this. Here are a few names, and from there, let's get to the core of it. So this is kind of the plan of my talk. I don't know if we are going to get to the quadruple, so the third part here, but hopefully I'll have some time still to mention one or two things. But the crux is really the first two parts. The first one is about the general relativity geodesics. So I'm going to remind you what we mean by a geodesic in GR, what is geodesic motion, and then we'll see how we can formulate geodesics as a Hamiltonian system. I'm also going to remind you of the general thing that we call a Hamiltonian system. And then from the Hamiltonian perspective, we can then speak about integrability or integrable systems. And once this is done for geodesics, we are going to ask ourselves, can we extend any integrability result, especially around black holes, to the case where things are a little bit more complicated, but also more realistic, in the sense that geodesics are not the correct description of the motion in GR, but we also have to take into account the spin of any object that can rotate around its proper axis. And then we're essentially going to do the same thing, discuss the Hamiltonian formulation and ask whether the integrability of geodesics can hold with the spin effects. So this is how it's going to go. And I'll first give you the general setup. So the general setup is this one. You can see a big black hole in the middle of the screen. So it's a rotating black hole. So in GR, we have nice unicity theorems that tell us that essentially any reasonable and isolated black hole should be a Kerr black hole. So a Kerr or rotating black hole is pretty much the same thing here. And around this big, massive black hole, we have this small object on the right-hand side. So by small object, I mean anything that's very small compared to the big black hole. So it can be a grain of dust, it can be a star, an asteroid, anything. I'm going to speak about mostly like a compact object, like a small black hole or a small neutron star, because this is the main applications of my work. But essentially, everything here holds for small objects around any black hole. And so, since we are looking at black holes, we have very strong gravitational fields, especially in the vicinity of them. So we need relativistic physics. And since we are interested in the motion of the small object, we require a notion of mechanics, and therefore the link between Poincaré and Einstein, just to quote them once more. So the question is, what is the trajectory of the small object? And as you have probably guessed, the answer is a geodesic. And probably the first time this was clearly stated and mathematically given was actually before the Einstein field equations were even found by Einstein himself. It was in a 1914 paper here. So it's in German on the right-hand side. The translation in English gives us the solution to the question. The trajectory of the small object is actually a geodesic of the four manifold that describes the black hole. On the right, on the slides, you can see probably one of the first occurrences in the GR case of the geodesic equation, if some of you are familiar with it. And on the bottom left, you have the modern version of the geodesic equation, which is written in covariant form, with essentially the parallel transport of the tangent vector of the geodesic. So that's it pretty much. The answer to the question is the trajectory is actually a Kerr geodesic. Of course, this is a very naive approach, but still it encompasses a lot of astrophysical effects. And let me show you how we can use this in practice. So we're interested in the motion of the small object around the black hole. So whereas this figure was rather like a space depiction of the issue with it's a photograph, it's a photo at a given instant of time. On the left-hand side here, you have a space-time diagram with the time flowing from bottom to the top, and two space directions, if you wish, which would be the orthogonal to the t direction. So the Kerr black hole now is a disk, and it exists everywhere alongside at any time. And the geodesic now is like an helix orbiting around the black hole. And this geometric picture has a very simple mathematical description. So you describe your big black hole as a space-time. So you give some coordinates on your space-time, and you give the geometry of the black hole through the metric or the metric coefficients here, which are just functions of the coordinates. So that's for the big black hole. And for the small object, then you have the momentum of your object, which is simply tangent to the world line or the geodesic here. And this proportionality constant between the 4 momentum and the 4 velocity is simply the mass of the particle. This is how we define essentially the mass in that case. And the motion is simply given by, so it used to be a postulate when Einstein thought about this, but of course this is just a consequence of the general theory of relativity, that U is parallel transported along itself. And this is another way of saying that the world line of this small object is a geodesic. So in practice, the way you solve this equation is you parameterize the world line here, which I've called L, with the 4 velocity being the differential of the position x, and then you solve the geodesic equation, which looks like this. So it's a little bit complicated, and the coefficients gamma here are just a nonlinear function of the x's itself. So it's a nonlinear equation, but you can still solve it in at least approximately most of the times. And so these 4 ODEs, you are now interested in writing them as a particular formulation, mathematical formulation, which we call a Hamiltonian formulation. So I'm now going to explain a little bit what I mean by this. So a Hamiltonian system, probably not the most general sense you can give it, but a fairly abstract and broad sense. You can define a Hamiltonian system with three ingredients. The first one is the phase space. So the phase space is essentially an abstract space where the trajectories of your object have a counterpart in this phase space. You also need some geometric structure on your phase space, and this is usually given as a Poisson bracket. This Poisson bracket essentially gives you all the necessary tools to do some geometry on the phase space, which is just a collection of points otherwise. And lastly, the Hamiltonian H specifies, so this is just a function of phase space coordinates, so like a scalar field on M if you wish. And this Hamiltonian, when you put it into the law of motion here on the right-hand side, it generates a number of equations, of differential equations, the solutions of which are the trajectories on your phase space, which I've depicted here in a very simple way. And for geodesics, so the top of the slide here is the generic setup for any Hamiltonian system. And if we want to rewrite our geodesic equations, which apply in GR, then we have to make the three choices that are at the bottom of the slide. So your phase space will be something that has 8 dimensions. It will be made of the coordinates on your space-time, sorry, and the conjugated momenta to it. And these conjugated momenta here are just the components of the 4 momentum of your particle in space-time. So this has a nice physical interpretation. The Poisson brackets that you choose with these coordinates are simply the canonical conjugated pairs that we all know and love if we followed any introductory course on mechanics at the university, let's say. So you can recognize on the bottom here the Hamilton's equation, which result from these Poisson brackets. And lastly, the Hamiltonian. So this is not a given. You have to look for it, but it turns out to be simply this formula here. So it depends on both the coordinates x and the momentum p. The x are just hidden in the metric coefficients. So if you have all of these ingredients, then you can do Hamiltonian mechanics. So I thought I'd give you an example. So this is the Hamiltonian in the case of not a rotating black hole, but a static and stationary black hole, which is called a Schwarzschild black hole. So it's just a non-rotating one. And this is the Hamiltonian. It has all of these coordinates and expression. And for example, if you look at the equation for the t coordinate, then you get something which may look familiar to you, that dt over d tau, tau being the proper time of your small object, is not a constant. Actually, it's not zero even. It's something that depends on the position. You can see it depends on the r variable, the distance to the black hole. And this is actually what we call time dilation, gravitational time dilation in that case. Another example, if you look at the equation of motion for pt, the momentum conjugated to t, then you get 0 because the Hamiltonian doesn't depend explicitly on t. And this is a translation of energy conservation. And another example perhaps is the equation for dr, dr over d tau. It's non-zero, but you can get it to be 0 if you look at the places where a PR is 0, for example. And this tells you that there exists, for example, circular orbits around a given black hole. Okay, so all of these equations are just here to show you that to study the space-time orbits, you can simply look at the phase space trajectories that are given by this set of differential equations. Okay, so this is yet again another link between the phase space and the space-time approach. On the left-hand side, you have a slice of your 8-dimensional phase space. So I'm not really concerned with the details here, just you can see that there are a number of curves here, and all of these curves are the solutions to the Hamilton's equation. And on the right-hand side, you have the equivalence of these curves in the space-time. So each space-time orbit, you may recognize some of them plunging into the black hole, some of them just orbiting around. They are in a one-to-one correspondence with the phase space trajectory. So you have this nice tool, which is called phase space orbits, which are mapped to the space-time orbits. Okay, and if you want to look at all the orbits possible, then you can also do so. In the case of the Schwarzschild geodesic, you can plot a diagram of the energy of the particle with respect to the angular momentum, and then you get all of these nice orbits and names, complicated names that people in relativity give to particular types of orbits. Okay, so this is just to motivate the Hamiltonian aspect of things. Now let's go to the crux of my talk, the integrability of the systems or integrable systems. And for that, let's go back to the Schwarzschild case again. So this is the Hamiltonian, and if you compute, as we saw earlier, if you compute the equation of motion for the pt components, then you'll find that it's actually constant. dpt over d tau is 0. So this means that this quantity pt, or its opposite, what we call the energy of the particle, is actually conserved. And this is always related to some kind of symmetry in the case of space-time dynamics, and also in the case of Newtonian mechanics too. This is simply a reminder that the vector dt is a Killing vector of the spacetime metric that describes the Schwarzschild black hole. And you can do this for other things. For example, if you look at the p phi component, that this equation of motion is also dp phi theta is equal to 0. And this you can relate to a particular axis of symmetry of the Schwarzschild black hole. So the Schwarzschild black hole is spherically symmetric. So any axis that goes through its center is an axis of symmetry. And this is the reason why this component p phi is constant. It's actually one of the components of the total angular momentum, which has also a conserved norm, as in Newtonian mechanics. And this is also related to other Killing vectors, 2 of them, more precisely. And lastly, the mass of the particle, if you pay close attention to the formula I've shown before, that this is just the Hamiltonian of the particle is also conserved, as is any Hamiltonian system in general. Okay, so here the key point is that all of these conserved quantities, these functions that are constant throughout the motion, are usually associated to some kind of symmetry at the level of the space-time. Here, some Killing vector fields, and perhaps, as we will see later on, other types of Killing objects. Now, what is an integrable system then? Well, here we have an example in the case of the Schwarzschild system. You can see that the phase space is eight-dimensional, so 4 coordinates, 4 momentum, and it has 4 conserved quantities: the energy, 2 angular momentum pieces, and the mass of the object. And having 4 conserved quantities for 4 coordinates on phase space means that you are integrable. So what is an integrable system in general is simply when you have as many integrals of motion, or first integrals, or constants of motion. All of these terms represent the same thing for me here. When you have as many of those as degrees of freedom, in other words, half the dimension of phase space. So there are a number of other assumptions to be had. For example, what we call an integral of motion is actually something that should commute with the Hamiltonian itself. So if you use the Hamiltonian equation, it just means that dj over d tau is equal to 0, but that's equivalent to having j commuting with the Hamiltonian itself. And also you have a number of other technical things to consider. For example, each integral of motion should commute with the other ones. So you should have pairwise what we call involution, or pairwise commutation. And also each integral of motion should be linearly independent as you take them as a set, because otherwise you can just use, let's say j is a constant of motion, that you can use j squared, j3, j to the 4th, and so on. And you would have as many as you wish, and that's evidently just a trick. Okay, so if you have constants of motion that satisfy these things, then you get an integrable system. So an integrable system, why do we really care about integrable systems? Let me just skip aside here. Well, maybe the main reason why we care is about one particular theorem, which is called the Liouville-Arnold theorem, and which essentially tells you that if you have integrability, if you have as many constants of motion as you can, essentially, then your phase space does not, it is very well structured. It has a nice, it can be written as a nice Cartesian product of tori, or things that are diffeomorphic to a torus. And in that case, this means that you can have no chaos. You may be familiar with this notion of chaos in physics. Well, integrability is kind of the anti-chaos case, right? Either in the Hamiltonian system, either you are integrable, and if you are not integrable, then you have some chaotic dynamics associated to them. And therefore, you cannot have this nice phase space structure in the case of chaotic dynamics. So for us astrophysicists, this means that we have a nice set of tools to be used. For example, the phase space structure means that actually all the orbits are well classified in some kind of parameter space picture. So this is the picture I showed earlier with all the orbits here. For example, this kind of picture, when you can plot all the orbits given some parameters, then this can only happen for integrable systems. Other consequences is the fact that if you are integrable, then you have some nice, very, very nice coordinate system on your phase space, which are called action angle variables. And they are related to, they have many advantages. One of them is that you can, in general, you can solve the equations of motion analytically, or at least by quadrature, using these variables. So this is always very nice. Then, thanks to these action angle variables, you have this notion, very well-defined notion actually of frequencies of the motion. And therefore, you can then study the frequencies and also their ratio, in other words, the resonances in astrophysical phenomena. And also, if you are not quite, if you perturb slightly an integrable system, then you have all of these nice theorems of mathematics that you can use to then add dissipation or add perturbations to the integrable system. So in other words, integrable systems are the best. Nothing is exactly integrable in physics, but most systems we're interested in are kind of integrable. They are close to it. And even those close to integrable systems, we have many nice and interesting things to say. Okay, so this is why I care about this system and why one should care about integrability. Okay, so let me then apply this to the case of the Schwarzschild case. So as I said, each integral of motion is related to a Killing field. So the Killing field is something which I call K here. It's defined as something that satisfies the Killing equation. So covariant derivative of K, take the symmetry, should be 0. And in that case, this generates an integral of motion. So this integral of motion in the case of Schwarzschild case, you can see here, we have 3 of them. Each one is associated to a Killing field. So I haven't written the one associated to L2, but you can find it easily otherwise. And in the case of a Kerr black hole, so again, remember, Schwarzschild is the non-spinning black hole, Kerr is the spinning one, rotating one. Then you only have 2 because you lose spherical symmetry, but you still have axis symmetry. So this is the Killing vector field d phi here associated to the z component of the angular momentum. Okay, so as you can see, we have this concept of motion for the black hole spacetime. And in particular, the Schwarzschild case is geodesic, is integrable. So now, what happens for the Kerr case? Well, initially the Kerr case was thought to be not integrable, not for long, because the Kerr black hole was discovered mathematically in 1963, I think, and it was proved to be integrable only 2 years later. So in between those 2 years, people may have thought that it was not integrable because you had less symmetry. The Kerr spacetime is less symmetric than the Schwarzschild one. Thankfully, people found out in the 60s too that there was something else aside from Killing vector fields. There were also what we call Killing tensor. Killing tensor is just like a Killing vector, but it has an extra indices on top of it. And from it, you can generate a number of other constants of motion. So in the case of Schwarzschild, actually the mass of the object, or the Hamiltonian, is, you can show it's related to this Killing tensor field itself. And the Killing tensor in that case is just the metric. It's very simple. And in the case of the Kerr spacetime, you have also the metric, but also another non-trivial Killing tensor, which is called a Penrose or Walker tensor. And this generates something called the Carter constant, which you may know. And the Carter constant is nothing but the generalization of the total angular momentum of the Schwarzschild case to the non-spherical case. And so both of these spacetimes have 4 integrals of motion. There are 4. All of them are in involution and they are linearly independent. Therefore, all the black hole dynamics are integrable. And this has been known since the 1960s. Okay. So since black hole geodesics are integrable, let's ask ourselves, can we go beyond that? How do we describe in a better way than just geodesics? So let's go back to our initial question. What is the trajectory of my small object around the black hole? So Einstein said it was a geodesic, but we know now that it's not a complete story, of course. In particular, if I plot a geodesic on this picture, it's now the gray dashed line. This is the geodesic. And the true motion of your body, if you were to let it go at some point on the left, then it will not follow the geodesic. It will be away from the geodesic, not too far, but there is difference between the position expected from a geodesic and the position expected from the true world line. And the difference can be made precise. So you can see that the geodesic has the parallel transport equation, but the accelerated true world line of the object doesn't. It has let's say, a force on the right-hand side of this equation. And in that force, you can have many other, there are many reasons why there would be a force there. And let me give you a quick overview of that. And this is essentially based on the fact that a geodesic, as Einstein showed us in his 1914 paper, it's only the motion of a test particle. So test particle, you have two words. Test means that it only feels something. It doesn't back react on the background. And particle means that it is really a point and it behaves like so. So neither a neutron star, for example, is neither a test object nor a particle. So it has non-test effects, which we call self-field effects. In other words, it back reacts on the background spacetime. This is essentially what generates gravitational waves, so it's pretty important. And it's also not just a point. It has extended properties, like it can spin on itself and it can also deform. And this is what we call extended body effects. So all of these kind of effects, we hope we have seen some of them in the past since the discovery of gravitational waves, and we expect to see more of them in the upcoming years with the new generation of gravitational wave detectors. But now I'm just going to focus on these extended body effects, not the self-field effects. So there will be no gravitational wave here, and the background will always be an exact Kerr spacetime. Okay, so let's do that in 3 times. By answering this question: what happens to Kerr integrability when the body is not just a point following a geodesic, but it has, let's say, a spinning degree of freedom, can rotate on itself? So we do this in 3 steps. First, we account for the object's spin. Then we describe it as a Hamiltonian system again, and try and see if we can find enough integrals of motion, just as we did for geodesics. Okay, so let me simply explain how we include the body spin. So let's zoom in on my small object orbiting the black hole. And here you can see it has a backpack in there. And in this backpack, you can see, and you will find that if you really want to be, just as Einstein said, you just have to input some linear momentum to the object. And this linear momentum is generally not, if you stop there, then the linear momentum will be tangent to the world line. It will be parallel to the 4 velocity. But if you add other degrees of freedom, for example, angular momentum of your object, so I'm really speaking about the spin of the small object here, then you can show that the linear momentum will not be tangent to the 4 velocity anymore. And you can also add other types of objects, like quadruples, for example, which encode the information about the deformation of your body, just like tidal deformations, if you wish. Or, for example, the centrifugal deformation, because the body rotates on itself, therefore it flattens at the poles. So all of these objects, all of these extra degrees of freedom, you can add to the description of your object. And in that case, the equation of motion will not be the geodesic equation anymore. It will be something a little bit more complicated. For example, it's actually what we call today the Dixon-Hartley equations, or some other names associated to these equations. And they tell you that instead of having just kinematics, like for the geodesics, you also have some dynamics on top of what's driving the motion. So this is, for example, the equation of motion for the linear momentum P. So remember, it used to be 0 on the right-hand side at the geodesic approximation, but now it has these 2 extra contributions. The first one is a coupling between the R ABCD here, which is the Riemann tensor. So this and it's contracted with the spin tensor of the object, SAB. So this is like a spin curvature coupling. So we don't have that in Euclidean Newtonian mechanics, but you already have that in the non-Euclidean Newtonian gravitational case. And this extra piece on the right, the red piece, the force, is just something that has to do with the deformations and other multiples of higher degree. And you have the same kind of equation for the spin of the object, which looks like this. So essentially, the spin of the object is driven by the misalignment between the 4 momentum and the 4 velocity, and also, again, something which is related to the higher structure of the object. So these equations are simply stated like this, but are quite complicated. I'm not going to give you any details on how to solve them. The only thing I care about, really, first of all, is just get rid of the dynamic part. So this means that we just truncate this expansion to just the spinning case. We don't consider deformations. And the other thing I want to do is simply describe it as a Hamiltonian system. I don't want to solve the equations right now. There are some people listening to this talk who know how to solve this equation very well. And I just want to describe it as a Hamiltonian one. So how do we do this? So again, it's pretty complicated. So I'm just going to give you a 2-slide summary of how we do this. So this slide is, again, no spin, just the geodesic case once again. So you can recognize on the left the ingredients, the phase space of 8 dimensions in the middle, and the law of motion on the right-hand side. And just as a reminder, the 3 ingredients that we chose for geodesics are at the bottom. So the Poisson brackets were canonical, for example. The coordinates, there were 8 of them. And the Hamiltonian was the thing on the bottom right. So now just to show you what happens when we go to the spinning case, so if we add spinning degrees of freedom to the now non-geodesic object, then everything that's in red has changed now. For example, the phase space has more dimensions. This is easily understandable. It's because all the spinning degrees of freedom which did not exist for the geodesic case now need to be accounted for in the formalism. So you have extra dimensions in phase space. The other thing, though, is that the Poisson brackets are not canonical anymore. So they are a little bit more complicated, but they are necessary to account for the new terms on the right-hand side of the parallel transport equations. If I can just show you one quick slide, on the left-hand side, you have the very complicated Poisson brackets with now the new spinning degrees of freedom S. And each of these terms will generate the right-hand side of the equations that now drive the motion of the body. So if you set anything that has a S here to 0, you'll get back the geodesic case. But if S is not 0, which is what we want to describe here, then you don't have as simple as the structure. Okay, so that's what we are now working with. And we now want to answer the question, is it still integrable, and can we find enough integrals of motion? So the new system has 14 dimensions. So we would need 7 integrals of motion if you count correctly. And yet I'm going to make the case that actually this question doesn't have a properly, it's not actually well posed mathematically. And I'm a bit short on time. So I'm just going to tell you why this is and show you with a picture how we solve these issues. So the first issue, is the fact that the new brackets that describe the dynamics, so these ones here, the complicated ones here on the left-hand side. So these guys, they are very complicated, and they have inherent degeneracies to them. These degeneracies, you can actually attribute them to the local invariance of general relativity, so the local Minkowski nature. And the other problem is the fact that the resulting system of ODEs is actually not well posed from a physical point of view. And this is because the spin in GR is complicated to define, but this is also the case in Newtonian mechanics. Essentially, the thing is, when you say a body is spinning, you need to say with respect to which axis it is spinning. And there is no natural notion of spin axis in GR compared to Newtonian mechanics, for example. So these two problems mean mathematically that the very question in red at the top is ill-posed. And the way we solve this, thankfully, and this is kind of the new thing in what we've done with my colleagues, is to implement these questions and find an answer to them in a very simple and nice geometrical framework. The degeneracies which lead to a degenerate system actually can be accounted for by the use of what we call symplectic foliations, essentially saying that you have these particular functions called Casimirs, which act against the degeneracies. And the problem of the definition of spin in GR, well, you can treat it with a different notion of Poisson brackets, which we call Poisson-Dirac brackets. And these are just mathematical tools that we can use to solve these two issues. So I'm going to stop that, so leave this away for now. And I'm just going to summarize how we use these tools to simplify the problem. So this is on the left our big phase space with now the spin degrees of freedom. You can see the extra spin dimension here. So of course it's 14 dimensional, so bear with me with the simplification here. And one thing we do is to solve the degeneracy of the brackets. Well, it essentially it's equivalent to actually looking at the subspace of this big phase space where we have fixed some spin degrees of freedom. So this lower dimensional phase space submanifold, if you wish, they are 12 dimensional now. And on this phase space, we also need to account for the definition of spin in GR. And this enforces us to look at yet another submanifold of the big phase space. So this is the one in black now. So this guy has 11 dimensions. And overall, if we want to solve both issues at once, then we have to look at the intersection of these two submanifolds. So essentially, what I mean to say here is we have these problems in physics or well-posedness of the ODEs, and we solve them by simply restricting our geometrical phase space to something which has less dimensions, but which still encompasses all the physical degrees of freedom and still contains all the physical orbits, which is the most important thing. At the end of the day, at the end of this process, we get a 10-dimensional phase space. So it's still 2 dimensions higher than the geodesic case. But in this phase space, we have no degeneracies, everything is well posed, and all the physically realistic orbits are well defined. So in that phase space, we can now talk about integrability. And I'm going to end up with the answer to our original question. And I'm simply going to say that the only thing left to do is actually work now in the correct phase space. So it is the case that, so we work in this 10-dimensional phase space here, where the object is allowed, the small object rotating around the big black hole is allowed to spin. We actually found, so people found already in the 80s some invariance of motion. We did not discover any new integral of motion on invariance, but everything that exists for Kerr can be generalized to the case of the spinning small body. So this is why the Q here has a 1 and at top of it. It's because it's not the Carter constant, but it's something which is a slight correction to the Carter constant. And all of these constants of motion here, they are all in involution with respect to the right Poisson brackets. So again, I've left this aside, but when you do Hamiltonian mechanics and you plunge onto a submanifold, you need to do this properly in regards to the Poisson brackets. So this means that we don't use the initial ones, we use the Poisson brackets that know that we are now on the red subspace. And if we compute all the Poisson brackets that we need to show integrability, so remember, Poisson brackets with H to ensure that it is an invariant, and Poisson brackets with among themselves to show that they are in involution. If we do this, then we get exactly the right result, namely that everything commutes. So this is just a screenshot of the mathematical notebook that does just that, because by hand is very complicated. And as a conclusion, the linear in spin case. So if the small body is spinning, then the motion is still integrable in the same sense as the Kerr geodesics. This is essentially the main result of everything here. Perhaps just to mention that we can go beyond that, let me simply say that if we now include the quadratic in spin case, this also works. So this is the same slide as before, but now we are going one level higher in the description of the small body. It is now allowed to deform on itself. It's not just a spinning top anymore. It's also a spinning top that can deform. And everything that I've showed here can also be done. So this works also in higher level than just the linear in spin case. So just to summarize and conclude, so in any background spacetime, so not just black hole spacetimes, when you add spin of your moving objects, it comes with a number of problems. The degeneracies I've mentioned. But you can lift these degeneracies and solve these issues by using tools that are well known. They've been known for almost a century now in the theory of Poisson systems. And the resulting system has just the right number of dimensions, 10, and it can be shown to be non-degenerate, and it is integrable in the case of a Kerr background. In other words, if you look at a small black hole orbiting a big black hole, in this particular regime where the small black hole is much smaller than the big one, then you have integrability, both for just a spinning top and also a deforming spinning top. Both cases are still integrable. And all of this is also related to some other kind of symmetry, just like I mentioned at the beginning, where symmetries resulted in integrability. Well, this is still the case with not a new, but a different version of a different notion of symmetry, rather. Okay, why is it important? Well, the first thing is for theoretical reasons. We keep bridging GR and symplectic geometry or Hamiltonian mechanics, and this is always good. It kind of also answers a conjecture in the literature, which was to had to do with the chaos of such system. Some people thought it was chaotic. Some people thought it was integrable. Some people thought it was not a well-posed question. Now it's pretty clear that it's the case that it is integrable. And lastly, we can now use all the tools from Hamiltonian mechanics, from action angle variables to resonances and so on. So the practical reasons, on the other hand, are about answering the question whether the chaos is important for the future of gravitational wave astronomy. Perhaps not, at least not for the extended body effects. Also, you have all of this branch of numerical integration that is called symplectic integration that could be used to improve the gravitational wave templates generation schemes. So that's left for future work, of course. And lastly, the integrability can be used to derive some very important laws that we use in relativistic mechanics. Perhaps some of you know about flux balance laws or first laws of mechanics. And these guys actually crucially depend on the integrability which we've just shown here. And maybe this will help the self-force community, which actually the other part of this whole project is extended body and self-field effects. And the two can communicate now with these new results, probably. Okay, I'll leave you to it. Here are a few references about details about the papers. And if you have any question, please, I'll be happy to answer. Thank you.
Thank you, Paul. Thank you very much for this wonderful webinar. Can you hear me?
Yes, I can. Thanks.
Awesome. Thank you. I don't see my mic level moving. Okay, thank you. This was very pedagogical. I love it. These are great results. Today, our webinar is also special because we'll have host. So I'll give it to Lisa, which will ask some questions from here and from the YouTube channel. Thank you, Paul.
Perfect. Thank you, Alejandro. Thank you so much, Paul. That was a beautiful talk and really beautiful work. So there are a few questions from YouTube. So the first one is, can you explain the foundation of the differential equations? So I'm assuming this is sort of alluding to where what I call the MPD equations come from and what they mean.
Right.
Could you comment briefly on this?
Yes. So these equations, of course, I've called them Dixon-Hart equations because I think we should call them that way now. But usually people also in my papers, I call them Mathison-Papapetrou, Dixon, Tulshiev equations, something like this. And these equations, essentially, they come from, so in the grand scheme of things, if you look at the conservation of energy momentum tensor, and you write for this stress energy momentum tensor a series of Dirac deltas, so that everything, all the energy and momentum is located around the world line, then you can show that the conservation of stress energy tensor actually leads in a very direct and one-to-one way to these two sets of equations here. You can see that we have 10 equations here because the equation for P has 4, the equation for S has 6 because the tensor SAB is antisymmetric. And these 10 equations are actually in a one-to-one relation to the 10 components of the nabla A TAB equals 0 equation of GR. So you can also derive these equations in a non-test object framework, accounting for the self-field effects. But essentially, it is just the result of a multipolar expansion in the GR context. So it has everything similar to Euclidean Newtonian mechanics, but of course, much more contributions on the right-hand side of these two equations. And maybe also let me add that I call them the Dixon-Hart equations, especially because the Hart part, so Abraham Hart has written these derivations of these equations, which are actually independent of the theory. They are kind of agnostic of the relativistic theory behind, in a way. And you can actually show that the Newton equations of motion, that they take exactly this form if you follow the rules that he has given. So this is just a byproduct of multipolar expansions of compact objects, let's say, in GR.
Beautiful. I might start calling them the Dixon-Hart equations as well. That's very nice.
That'd be
nice. Okay. So another question on YouTube is, what are the natural units at the level of the space-time? So perhaps this is, some form of geometric units. Maybe you can elaborate
yes.
on. Yeah.
Yeah, of course, I should have mentioned that. Sorry. So yeah, as very, very often in when we do this type of calculations, we use geometrized units where the Newton constant is equal to 1 and the speed of light is also equal to 1. So this allows us to not really have any dimension in all the equations. Everything has just so time, space, and energy all have the same equation, and mass to have the same dimension. But you can revert to any choice of coordinates you like just by doing the revert process. Of course, sometimes we want to go back to especially the G over C squared terms to see where, let's say in a post-Newtonian or post-Minkowskian framework, you can get rid of some terms or compare terms with one another. But in this case, where we're purely relativistic, there is no post-Newtonian approximation. Anything is strong field, so we just use G equals C equals 1. Yeah.
Beautiful. So I think Alejandro has a question. Do you want to go ahead and ask?
Thank you, Lisa. So I have many questions, and I have briefly spoken to Paul. This is amazing, but I would like you to say to ask you if you can comment on the implications for the comparable mass black holes. Is there anything we can learn from this way of writing the equation and analyzing the system, but in the case for comparable mass black holes?
Right. So it's pretty well documented now that so this work would be I would say more in the Emery case, so extreme mass ratio in spirals, except that it doesn't have any self-field effects. It's just about the extended body effects. However, we still have this strong, like the fundamental principle behind all this is that the body orbiting the black hole is much smaller than the black hole, right? This is the main reason why you can actually forget about self-field effects in a way. And this is the reason why you have this multipolar structure in the first place. Now, if you want to go to the comparable masses case, then you are, by construction, violating the very foundations of this framework. So that doesn't mean it will become useless or wrong in any way. It's been well documented now that even the Emery case, so the small mass ratio limit in the limit where both masses tend to 1, then many results, let's not say most, but many results still hold when you have large mass ratios. So it's definitely the case where the mass ratio is not that small. And it's actually one of the ongoing projects that people pursue now is trying to understand why this non-extreme mass ratio limit works so well even in the why the Emery limit works so well even in the non-extreme mass ratio limit. But I would just have to give you a bunch of papers which have performed a numerical analysis and comparisons between the Emery and non-Emery cases, finding very good agreement. But yeah, ultimately this whole framework is built in the Emery or at least small mass ratio assumption. But it turns out that when you try to apply everything to the non-small ratio, then it kind of works too in a very specific way. So I'm not a specialist on it. I would give you more references if you needed.
Thank you, Paul. And then just to see if I understood. So in principle, if I go higher in the multipolar structure, then it is unclear what's going to happen, right? Or do you have any expectations about the integrability character? Or like, what happen if let's say I don't do these expansions? Like if I were able to put this on a computer and I can solve it fully non-linearly, even in the extreme mass ratios case. Let's say I can do M-Vis on the computer fully non-linearly. Is there any expectation?
Okay. So you mean comparing like numerical relativity of a small mass ratio compared to this framework?
Yeah, and then yes, and then if there will be, for example, signatures of chaos or something, because in some sense this is valid to the first leading order, accounting for properly for staff, right? But then,
yes, yeah,
yes. So that's my question.
Okay. Yes. So you may know. So we have all of these. So in the relativistic two-body problem, regardless of masses and orbital separations, we have all of these. Like we have a plethora of schemes. I remember perhaps the one that encompasses everything is now called Tutti Frutti scheme. If you look through it, so So it shows the whole zoology of different methods to attack this difficult problem. One of them, of course, is the Emery assumption, where one object is much smaller than the other one. The other one would be the post-Newtonian or post-Minkowskian, which works for a weak gravitational field or large orbital separations, things like this. And also you have the full numerical relativity case. So all of these schemes, they don't have a nice, definite split between them. They overlap quite much in pretty much in all directions of parameter space. Some of them are more, so at the end of the day, you compare everything to numerical relativity because you know that it's just the pure Einstein equation giving you the solution. But we still do these approximations framework. And so far, everything that has been compared, both in the Emery case or the large orbital separations case, and everything comes out to be fairly consistent, even I would say very much consistent, even in parameter space regions where you would not expect these overlaps. So I'm not sure I'm answering your question, but yeah, all these schemes very much agree with one another both in the region of parameter space where they are expected to agree, but also sometimes other parts of phase space.
Yeah, but to clarify, my question was more related to integrability. So it could be that the system is integrable at the level that you're studying. And then I got to higher, but then the chaos or the non-integrability is so tiny that it's really not relevant for the motion. It could be, right? That's more my question.
Yeah. Okay, I get your question now. So regarding integrability, so in this Emery case, this integrability is proven, no question. I think this is clear now, especially at quadratic order in spin when you only have a small black hole orbiting the big one. If it's something else than a black hole, then it's not, a priori, it's not integrable. Now you can do the same calculations in the post-Newtonian regime, where you also have a Hamiltonian framework, and you can also ask about integrability. And it turns out that the results presented here and those by Leo Stein and Shashwat Tanay about the post-Newtonian integrability, they match. I mean, given the post-Newtonian counting and the modeling, they match. So it's fairly consistent too. After that, even just to speak about integrability, you need a Hamiltonian framework. So I'm not aware of any integrability feature of the Hamiltonian formulation of numerical relativity, for example, because there is dissipation there and it's not even clear that it's a conservative system.
Yeah.
And also at the end of the day, I didn't have time to mention that, but I want to point out something important is that we all speak about, so I've said that like 20 times now, that the motion of a small object around a big black hole is integrable. What I mean by that really is not that the physical motion is integrable. Like integrability is a feature of a mathematical system. So I have this slide here. Maybe it's nice to just and one shall not for there it is. The paragraph on the bottom. Oh, there. On the bottom here, the first line of the second paragraph, integrability really is a mathematical notion, right? So you could say a pendulum is integrable, and no one would disagree with you, and yet a pendulum is not integrable. It's just a particular model of a pendulum that is integrable. So really, depending on the mathematical description you make of a system, you may end up with a integrable, not integrable system, even just non-Hamiltonian formulation. Like the full two-body problem is not Hamiltonian in the classical sense. It has all of these gravitational waves. It's non-local. It's a mess. So everywhere we can have a Hamiltonian conservative formulation, it seems that integrability follows. Otherwise, it's a very hard question.
Thank you.
Yeah, no worries.
Okay, I have a few questions. So you sort of alluded to a few things at the beginning of your talk, but I don't think you had time to talk about everything. So I think sort of following on from Alejandro's question, could you comment on like the existence of a generalized Carter constant for like quadrupolar test bodies and like any plans you have for this as a next step?
Yes, sure. So okay, so let me show you. So I mentioned that the constant of motion I use to show the linear in-spin integrability, they were known since 1981 and 82 by a work by Rüdiger. I'm sure you know about Rüdiger. Actually, the constant, we refer to them as Rüdiger constants. So here are the expressions that you are well aware of, I think. And this constant, they exist, they've been around for 40 years. At the next level of multipolar expansion, when you need to include quadratic in spin deformation. So the quadratic spin deformation, we use this quadruple tensor at the bottom here. You can see the two copies of the spin, and therefore the quadratic in spin notion. And in that case, okay, let me just move all the faces of the participants because I can't see the constant otherwise. Okay, there we go. Can you still see my screen? Yes. So on the right, on the last column, you have the quadratic in spin case. So all the constants of motion which are related to Killing invariance, they remain. So they date from actually maybe prior to Dixon's 64 paper. But then in 2023, Adrien Druard, Geoffrey Compère, and Justin Vines, they used the same algorithm that Rüdiger used in 1981, plus some very clever tricks about the Kerr spacetime itself, to show that actually the two Rüdiger constants, you could still get them at this order, at this quadratic in spin order, except for two things. The first thing is that it crucially depends on the SSC you use. So you have to use the TD-SSC. So everything I've done here is the TD-SSC case. And also there are, okay, three conditions. The SSC conditions. The second one is that the small object be a black hole. If it's not a black hole, then, okay, let's be precise here. It should behave as expected for a black hole because there is no proof that the black hole has this. There's just this convergence of results. And the third condition is that you are okay with these constants being conserved up to cubic in spin order. Right? They are not constant like the Dixon constant, for example, here. So these are the constant of motion that I've used to show quadratic in spin integrability. So okay, I don't know if that was the question, but
yeah, no, that's
one.
Perfect. Yeah, oh, go ahead.
Yeah, one extra comment is that the Rüdiger constant that is just linear in spin here, the thing I call K here, so Levi-Civita times Killing-Yano times spin tensor, this thing is also conserved at quadratic order in spin. It doesn't require any quadratic in spin correction. And okay, so all of these mysteries, we are currently investigating them. We don't really know why it is that it is the case. It has to do with the specialness of Kerr, of course. But we are currently in the middle of just brute force calculation to see whether this holds for other spacetimes than Kerr. It doesn't seem to be the case. And also to understand why it works for Kerr and not for other spacetime is also something we are trying to investigate. Perhaps one last thing, which was actually striking, was, okay, so the Dixon invariance related to the Killing vector fields. So these guys are constant of motion on the whole phase space. Like they don't care about the SSC, okay? So they really are, they are constant of motion for this 14-dimensional phase space on the left, the blue one. As soon as you, so if you look at the Rüdiger constant, they are not constant of motion for this system, okay? And yet they are for the Q constant of Rüdiger. In other words, just like the Carter constant, they somehow, this Rüdiger constant, they know that they are related to something that has to do with the Killing symmetries, the Killing vector field symmetries. And so they are still constant of motion on the blue phase space, gotcha. Which is really unexpected. I mean, so if you go back to how they were derived, they relied on the existence of the TD-SSC, and it turns out that you don't care about the TD-SSC. They are still conserved in Kerr, even without the TD-SSC. So that's really a mystery. Yeah. That's really a puzzling thing.
It's fascinating.
And many people are, I've told this to many people, and no one has a clue as to why this is the case. And we are trying also to elucidate this with Adrien and Justin. Yes.
Makes sense. Thank you. That was super interesting. Maybe one final question, if that's all right, Alejandro.
Sure, please.
I wanted to ask you about how you plan to interface like self-field and self-force effects with your Hamiltonian formulation, because you sort of alluded to that a little bit. Do you have any concrete ideas about how this will work or any plans? I'd be really interested to hear.
Right. So that case is really non-trivial.
Yeah.
So there have been some papers out there, papers by Francisco Blocco and Iana Flanagan, and also people now in Southampton. They have started to look at the Hamiltonian aspect of self-field effects on top of geodesic. So one difficulty is that as soon as you add the self-field, then you have non-local in-phase space effects. In other words, you have to have some preferred geodesic in your phase space, and then you have this notion of pseudo-Hamiltonian systems, which I'm not very familiar with. I need to do that. What I know for sure, actually, is I don't think, no, not for sure, you're never sure of anything, but I'm pretty sure there is no equivalent of integrability and Arnold-Liouville theorem for these pseudo-Hamiltonians, for these generalized notions of Hamiltonians that can account for the self-field effects. So it may be the case that actually whether it's integrable with the self-field makes no sense as a question, as a mathematical question. That could be the case. That may not be the case. I really don't know, but that's something I'm interested in for sure, because this is the next step, right? So we have this quadratic in spin extended body framework. If we can add the self-field effects, then essentially we have all the things we care about for, at least for LISA, for the space mission LISA, and of course doing that would be, but it's really complicated. As of now, those two frameworks, so the one I presented here without self-fields and the one that people use with the self-field but no extended body effects, they're pretty far apart. They really don't use the same tools. We might call them Hamiltonian frameworks, but they really rely on different mathematical tools and assumptions. So yeah, it's definitely one of the most important things I like to do in the coming years is to understand and bridge these two frameworks, of course.
Totally. Me too. Yeah, that's awesome. I'm glad you're thinking about
together,
it.
Then.
It's a hard problem.
Yes, it's very complicated.
Well, was there a question from Joel?
Yes, I have a very basic question because I'm completely lost. It made me feel completely like an undergraduate, being from another specialty. So I was wondering, you skipped a couple slides regarding the issue with spin in general relativity. I was wondering if you could give some detail on this, because you mentioned at some point in the conclusion some degeneracy. And of course, there's always the thing that about the double cover of spin. I wonder if it's related to that or if it's something else.
Yeah, I can give you. I can show you what I would have shown if I had if I had been quicker. Yes, sure. So the two issues I mentioned. So one of them really has to do with the Hamiltonian formulation. The other one really has to do with the physics of the problem. So the one with the Hamiltonian formulation, okay, let's start with the one with the physics. So in the multipolar framework we use, the spin, degrees of freedom of the object, is encoded into a antisymmetric two-tensor SAB here. And this guy, you can think of, given any time-like direction, you can decompose this antisymmetric tensor into two 4 vectors, which you would call the spin 4 vector, and the other one would be something that we call the mass dipole, because it has to do with whether you are away or close to the center of mass of the object. So you can either write everything in terms of the big SAB or the two 4 vectors S and D here. And as it turns out, if you want to have a well-posed and as many equations of motion as you have unknown in your problem, then you need to specify a reference frame where the mass dipole vanishes. And if you think in terms of Newtonian mechanics, this is just saying, okay, let the center of mass be the center of the coordinates in some sense. So this is also a problem that arises in Newtonian mechanics. It's just that in Newtonian mechanics, since we have an affine vector space, we don't really care about the choice. We just always take the center of mass because it is uniquely defined. But in GR, you don't have an affine vector space, so you have a choice to make. So it is conjectured that any choice you make should lead to the same physics. It is far from being proven and far from being harmless. especially when you go to the quadratic in spin case. And therefore, this is very important here that I mentioned that everything I did was under a particular choice of center of mass fixing, which is the one that's at the bottom here. You can see I've chosen the frame that is aligned in the time direction with the form momentum of the particle. It may be the case that if you choose another frame to define the center of mass, then maybe you don't even have a Hamiltonian framework, and maybe it's not even integrable. That's really an open question as of now. So that's one. So that's something that has nothing to do with the Hamiltonian framework. It's really about physically selecting the model and making arbitrary choices. But now this arbitrary choices has a counterpart. As you can see at the bottom, this choice is just an algebraic equation. It's a product of the P with the S is equal to 0. It's not an ODE. Hamiltonian mechanics really has to do, it's just an ODE system. So as soon as you make this choice, then you end up with an algebraic plus ODE system. And so you need to take account of this. And the way you account for this is, so your big phase space blue here on the left-hand side, you only want to go to the submanifold where these algebraic equations hold. So it defines a new phase space. As you can see, it's written here. It's 11-dimensional, and you can then study the motion in there. So that's to enforce the center of mass condition. So that's one issue. The other issue is that if you look at the 14-dimensional phase space and you look at the brackets that you have to use to obtain the right equations of motion. So again, these brackets, they're really like, they're kind of axiomatic, right? They essentially, you chose them such that the equations of motions are the ones that you wish. In other words, these ones, okay? You have to choose those brackets in such a way that these equations remain true. So if you choose these brackets, you have not much freedom. Actually, you have no freedom. You have to use these ones. And these brackets here, you can show that they are singular or degenerate in the following sense. There exists some function of the phase space coordinates which always commutes with anything else. Okay, it's what we call a Casimir invariant. And in the physical side of things, it's simply the norm of the spin and also something else. So there are two Casimir invariants here, and both of these quantities, they commute with everything. So you could say, well, they're just like first integrals of motion, but that's not the case, because the theorem about first integrals really states that it works for non-degenerate systems. And the very existence of these Casimir functions means that you're not really doing like Hamilton geometry, you're more doing Poisson geometry. It's really the field of Poisson geometry that we're working with here. Thankfully, and this is what I meant a bit quickly, if you look at the spaces where both of these Casimirs are constant, well, you can show it's a very nice and general theorem in Poisson geometry that they define the foliation of your phase space. They are like the level set of these Casimirs, and those level sets, they are perfectly fine. They are perfectly regular and non-degenerate. So you can just work on there and forget about the degeneracies, but it's still something that you have to do, because as you do that, you reduce the dimensionality of your phase space, and therefore it becomes easier to find integrals of motion. And of course, you have to do both things, both problems. So you need to look at the intersection of these two guys. So you have to look precisely at what happens to this intersection, because intersecting 12 and 11-dimensional phase space may give you anything from 0 to 11 dimensions. It turns out it's 10 and everything works well, but it's a key part of our work. It's to have been able to elucidate this particular interaction between the SSC, so the center of mass condition, and the degeneracies and so on.
Okay, I need to think a lot more about that. Right, yeah. Because yeah, okay. So from my point of view on your first part, you're kind of like fixing the gauge. And
yes, exactly.
Then yeah, and on the second part, I'm trying to understand what the role of the Casimirs are, because the Poisson brackets for the spin in the quantum mechanics point of view, they're just the how you define the generators of Lorentz transformation in right. So I'm thinking about the Casimirs now because if you have Poincaré invariance, you usually have the two Casimirs that are the mass, and then the one that's related to spin, and then having a second one, I'm not really sure what to make out of it, right?
Yeah, so actually these brackets here, these brackets for the spin, they are actually the SO13 brackets.
So it's one of those, the equivalent of the norm of the Pauli-Lubianski.
Yeah, exactly. Yeah.
Exactly. And then the other one, what's the other one then?
It will be the norm of the norm of the. So okay, if you write the spin vector and the Pauli-Lubianski vector, then one of them is squared of the spin minus squared of the Pauli vector, and the other one is the dot product of the spin with the Pauli vector.
Oh. Okay.
Oh, yeah. So these are the two. All of this is very well known in Lie algebra, probably in quantum mechanics too. And in this case, they just come up as Casimir invariants that you need to use. But of course, this is just the symmetries of the local symmetries of the Lorentz group, which are everywhere in spacetime. We need to account for them at some point.
Okay, then I need to go back to some textbooks. All right. Thank you very much.
Thanks.
All right, I think that we are now at the end of our webinar. Thank you very much, Paul, for this very interesting talk, and to all the participants who had questions through the YouTube channel or here in the room. Thank you for watching today this webinar, and of course it will stay on the YouTube channel for you all to rewatch it and send it to your friends. And to you all, we invite you to subscribe to our YouTube channel and X or Twitter accounts, Facebook, etc. And please make sure to connect in 2 weeks for our next webinar, which will be given by Rodolfo Capdevilla on muon colliders. Thank you all and have a great rest of the week. Bye-bye.
Bye.